statistical mechanics for molecular systems, and in the end, we introduced a formulation that allowed us to calculate equilibrium constant. I call it microscopic equilibrium constant. It's not thermodynamic equilibrium constant. They are connected, but not exactly the same. Okay. But anyway, it's we know how to calculate equilibrium constant and how actually we can define an equilibrium constant from a microscopic point of view. Basically, tell me Hamiltonian of the system using quantum chemistry. I can calculate the energy spectrum of a system. Ideally, of course, quantum chemistry has its own problem. For most molecular systems, it's not that trivial to calculate many molecules. If you have many molecules, to figure out energy functions, actually not that trivial. But anyway, assuming we can do that, and if you know energy function, you know E nu, meaning you know all the microspace, you know energy of all the microspace, then you can calculate partition function. And once you can calculate partition function, you can calculate all sorts of thermodynamic variables, including equilibrium constant. Okay, and so that along the line we made several approximations. We approximate a system with many molecules to be. We assume those molecules are not interacting with each other. So independent molecules. We assume the simple models such as harmonic oscillators and rigid rotors are applicable for molecular systems. But anyway, we came up with an equation to calculate equilibrium constant and to define equilibrium constant. And with that knowledge, we can finally calculate rate constant of a reaction. So this is actually the meat, the very important part of this course. Today we are going to talk about chemical dynamics. We finally we have the tools to talk about chemical dynamics. And actually, when I say chemical dynamics, I mean understanding the behavior, time-dependent behavior of a chemical system with microscopic knowledge. We use the structure, the fundamental physical constant, physical laws of quantum mechanics or Newtonian mechanics to understand the time evolution of a chemical system. This is in contrast to so-called chemical kinetics. So normally when I say kinetics, I mean a macroscopic behavior of a molecular system. So it's empirical. The change of concentrations are measured in experiments. Okay. So this is from microscopic dynamics, time-dependent behavior of molecules. This is essentially a very difficult problem because you need to, for a molecular system, you need to follow microscopic motions of many particles. Okay, and it's complicated. It's not easy to do, and we with appropriate approximations, we can get reasonable results for this. So today we are going to cover the basic theories for chemical dynamics. Next week we are going to give examples specifically for how we calculate rate constant for gas phase reactions. This will be, examples will be in next week. Okay, and then we'll have the second midterm. Okay. Yeah. Oh, by the way, I uploaded another homework yesterday. So there's homework number 5, but it's actually an exercise. You don't need to turn in your answers. Yeah. It's an exercise that covers today's and next week's content. Okay, where I give several problems. to help you prepare for the second midterm. So calculate rate constant microscopically using fundamental physical rule. It's a very difficult task. And we need to make many approximations in order to do this. There are several ways to consider this question, this problem. I'm going to talk about 4 different ways to treat this. Basically, calculate the problem, the essence of the problem is calculate. Microscopic principles. There are several ways that would allow one to do this. One is collision theory. So collision theory considers this problem from a kind of kinetic point of view. By considering the time evolution, the exact time evolution of particles, and consider chemical reactions as collision between molecules, and using this to figure out how reaction occurs. Second way is through transition state theory. Transition state theory is based on statistical mechanics. It assumes some fundamental properties of a reaction. Then based on those assumptions, you can treat the process of a reaction, reactant became products, as some quasi-equilibrium between your, I'll explain this in details later, between your reactant and your some transition state. So it's a statistical point of view. There's no detailed time evolution of a particle, position, and momentum. No, nothing like that. In this case, we use statistics, thermal equilibrium properties to figure out reaction rate. Nowadays, you can also use real molecular dynamic simulation. We have powerful computers. So given a molecular system, you can simulate, you can use either Newtonian equation of motion or quantum mechanical equation of motion, meaning Schrödinger equation, to propagate dynamics of molecular system. And then from the how reaction happens in those dynamics. So you follow the time evolution, you prepare the system in some initial condition, you use Newtonian mechanics or quantum mechanics to evolve the system in time. So you have a position of all atoms as a function of time. We call this a trajectory. And using those trajectory, you just sit there and look at how these molecules evolve. You can see the probability of a reaction. Okay, and then you can figure out rate from one set of atomic geometry to another set of atomic geometry. Now, it's called simulation because it's actually very much just like doing the experiment in computers. The problem of this methodology or this approach is we have a limited computational power, so you cannot treat a very large system. You can only treat small systems.
And usually chemical reactions are we so-called rare events. In many collisions, maybe in 10 to the 10 times collisions, reaction only happen once. So you spend a lot of computational power to look at the trajectory, but most of the trajectory are not does not transform your reactant into product. Those are very rare events. So sampling is a problem. Okay. Yeah. But anyway, you can do this. We're not going to go into details about this, but I just want to mention so one can do this nowadays using simulation. For some chemical reactions, you need to consider quantum mechanics explicitly. If you have, for example, if you have tunneling reactions of light particles, hydrogen, for example, hydrogen atom transfer, you need to consider quantum mechanics. Or in some reaction, for example, in chemical reaction, redox reactions, you have electron transfer, right? So in those electron transfer reactions, redox reactions, electrons are light particles. You need to use quantum mechanics to describe it. In that case, one must actually use quantum mechanics, and we need to use so-called quantum time dependent. Quantum time dependent perturbation. For example, electron transfer. Energy transfer. Quantum mechanics. But this is also a situation that covers actually a very broad range of important chemical reactions. Electron transfer, redox reactions, they are important. So this I'm not going to go into detail. Right? I'm going to just tell you, nowadays you can run simulation in computers to figure out reaction rate constant. It's possible. And not only it's non-trivial, it's not just you run the dynamics and then you get the rate. It's impossible because to sample real events, you need some spatial techniques. Okay, but it can be done. It can be done. If we have time, maybe in the last lecture in this semester, we are going to talk about this. Okay. I'll probably cover a little bit on so-called markers theory for electron transfer. And it's important nowadays, for example, if you want to understand photophysics of some organic materials in light emitting diode, in photovoltaics, organic photovoltaics, okay, electron transfer, energy transfer are important. So if you know some basics of how to think about those reactions, it will be good. But at this point, we are going to focus on these two. And actually, we are going to focus on these two with simple I mean, at this stage, at this point, we are going to focus on simple collision theory and simple transition state theory. I mean simple because we don't have time to cover the full range of even those theories here. So for collision theory, we are going to only cover collision between hot spheres, simplest one. And for transition state theory, we're going to only cover so-called simple transition state theory. It's simple path and no recursive type of transition state theory. Simple. So that will be the topic of today's lecture. Okay. So let's begin with collision theory. Last year we covered these two topics in chapter 19 in his textbook. I'm going to cover this part basically following the reasoning or the procedure in Sylvie's book with a little bit modification that I try to kind of condense it a little bit, try to make it even simpler. Okay. Actually, collision theory would be the most natural way of thinking about chemical reaction. And you learn about collision theory already in high school, but only in a qualitative way. I mean, you know, molecules have to collide to have a chemical reaction, and in collision, you have ineffective collision where this molecule collide and then bounce away, nothing happens. Okay. And to have a chemical reaction, you need to have molecules collide with a specific orientation, right orientation, and then enough energy to close so-called the activation energy. Then you have you can generate the product. You learn about those ideas in high school already. But a quantitative formulation of a collision theory, I mean, if you want to actually calculate reaction rate based on collision theory, it's a very extremely difficult, extremely complicated task. Actually, in the development of statistical mechanics, meaning to understand thermodynamic properties from microscopic properties, Boltzmann start with a so-called Boltzmann's kinetic equations. Boltzmann used this kind of kinetic point of view, basically using Newtonian dynamics. He write down equation of motion for many body system. All the molecules evolve in time following Newton's equation, and try to write down thermodynamic properties from there. He failed. He had a very limited success in this test. But later on, Gibbs or other scientists basically forget about Newtonian dynamics, forget about all the time evolution of particles, and focus on statistics, and then successfully kind of generated or constructed nowadays statistical mechanics. Yeah. And this is how I introduced statistical mechanics to you. Okay. So this is similar. If you want to understand chemical reaction, although it seems very straightforward to apply collision theory, but in reality it's too complicated. We can only work with hot spheres. So we'll focus on hot sphere conditions and use some basic results we already derived before. So we talk about how particles can collide with each other and have probability of those collisions. We talk about collision density already. So collision density, let's start with this. That we derived the number density of two particles collide in a bus depends on the density of the two particles, particle 1, particle 2, their number density, times pi d12 squared. d12 is the diameter of particle 1 plus diameter of particle 2. This basically defines the range for the collision to happen. Okay. And this pi d1, this is basically the cross section, pi r squared, the cross section for the collision to happen. And we have average relative speed of the two particles. And we also say that this average relative speed actually will be squared. Average speed of particle 1, average speed of particle 2. We talked about this already 2 weeks ago. So, if we consider this, then consider V1 plus V2. You can see. And what is the product we don't actually care? Actually, what is the product we don't actually care? C plus D or C plus Y. We don't really care. But we care about two particles collide. And those are structureless half-sphere particles. Okay? And the rate of the reaction defined as concentration will be time-dependent. Change in the concentration of V would depend on, well, how likely they collide with each other. Okay. So it's definitely proportional to Z1. Oh, sorry, this should be Z12. Collision density between two particles, two body collision density, Z12. And definitely it will be Z12 divided by NA is Avogadro number. So this is to make the quantity per mole per time. Z12 has already the time per second actually unit in it. So definition of this is how many collisions happens in this box. Okay? Yeah. And but to calculate the rate, we want to have a more quantity. So we divide this by Avogadro number. Okay. But here we already made an assumption. We assume each collision is a success reaction. So we assume that the successful rate of collision to make reaction is 1. So success. And there is a technical term for this. This is something is collision control. So for some radicals, this is a good approximation because in very reactive radicals, the collision to form a bond basically is barrierless. Barrierless means there's no activation energy in it. Okay. So we begin with barrierless collision control reaction. So each collision generates the product. The success rate is 1. Begin with this. Then we plug in this question. So we have Avogadro number I V12 square V12 minus. Then rho 1 and rho 2 are number densities. So they are volume number of particle 1, volume number of particle 2, number of V1 and number of V2. And what we like to do is we want to make this into concentration. Okay. The way we do it is we multiply this we move this here, but we need another Avogadro number here. So this will be, and when divided by volume, you have the concentration for that part. So this then became, this one goes with this one. So we have Na I d12 square d12 times V1 concentration, V2 concentration. Right? So this is the constant. So from the simple condition theory, we derive that the rate constant for bimolecular reaction A is simply a Avogadro number times pi V12 square times V12. We can further calculate this because we know this is the average relative speed. And it's simply the average speed by use the mass of the particle, you know, the reduced mass of the system, relative, internal relative speed. So we know pi d1 square root of 8 kVt pi. This is a reduced mass. Reduced mass. In this case, it's for V1, V2. So we have a microscopic expression for the rate constant. But of course, this result does not really describe the real rate constant, the real reaction. Actually, it's very often is very, very far away from the real rate constant, major is related. And very apparent, very clearly, this assumption of success rate equals to 1 is the biggest approximation here. Most reaction, you have activation energy. The collision need to overcome some barrier in order for this reaction to happen. So we need to include that into our expression for rate equation. So this is not enough. We need to refine this by consider effective collisions. One way to do this is simply plug in some number, kappa, smaller than 1. So basically this is an upper bound. This is the upper bound. And very often it is higher by like 3 orders of magnitude. Because very often, depending on the shape of the molecule and the activation energy, very often only one success reaction in like 1,000 collision or even a million collision or even more. Okay? So this is a very, very strongly overestimated value. Yeah. It's not good. No, we need to consider, at least we need to consider activation energy. So we need to treat the reaction in more detail. And the way to do this is to consider how energy transfer when a collision occurs. So let's consider two molecules or two hot spheres collide with each other. So let's say you have one. So their center let's say you have V1 and V2. We consider relative velocity, so we can assume that V1 is sitting here, not moving, and V2 is moving towards V1 by a velocity V12. Okay. So when V1 and V2 they are away from each other, there is no interaction. What happens in that stage is irrelevant to the reaction. What's relevant is only when V1 and V2 collide with each other. And then when V1 is here. Okay? So when V1 is here, the center of mass between V1 and V2, the center of them is connected by this line here. So let's say, let's define a few things. Let's define this as alpha, angle alpha. So when they collide, we still have this V12 along this direction. But this V12 must be divided into two components. One is, let me see. One component is VR. Okay, I'll try. So the critical, here is a critical thing. V12 can be separated into two components. One is along this center line, and another component is perpendicular to this center line. I'll call this component that's along the center line VR. What's important here is when they collide each other, the force between them is act along this center line. Okay? It's hot sphere. There's no friction between them. So there is no force tangent to the center line. You can have a force only along this center line. So this is the, when they collide, this is the direction for the force. So this component is along the direction of the force. Along the direction of the force means along the direction of energy transfer. What I'm saying here is, this is the portion of the kinetic energy that can be transferred between these two molecules. This part, kinetic energy along the direction that's perpendicular to the center line cannot be used in chemical reaction, basically. Let me repeat this again. When they collide, there is a line along the center of the two spheres, and this is the direction of the force acting on this molecule and on this molecule, basically the force between it. Okay? Only half sphere interaction. So this is the direction that energy can be transferred into the molecule. Initially, you have a total kinetic energy of this amount defined by this velocity, but only velocity, only kinetic energy along this direction can be transferred between these two molecules to be used for chemical reaction. And this part, this tangent velocity, is useless. This is the key idea here. So what we are going to calculate is, we want to consider the amount of kinetic energy that can be used for chemical reaction. In this collision situation, normally we define another parameter here called V. V parameter is called impact parameter. Impact parameter. And its maximum is D12. So this V must be smaller than D12. If V is longer, higher, bigger than D12, then there's no collision. Nothing happens. So for a reaction to occur, V must be smaller than D12. And using the same argument, I can say that when V equals to D12, there's no chemical reaction. They just pass each other. Nothing happens. Because this half sphere, there is no non-range interaction, nothing like that. Okay? In my note, I define this as VK. Let me change. Let me change the notation a little bit. Let's call it VK. So VK will be V12 times cosine alpha here. So this is alpha angle. So this component is cosine alpha. Okay? And we want to rewrite this into this V factor. So action K is defined as kinetic energy. Useful for reaction. So available kinetic energy for reaction will be F mu K squared. That's my argument. Only the kinetic energy along this center line, along the force, direction of the force, can be used for chemical reaction. And this will be F mu, let's plug this in, U1 square, cosine alpha square. And this part cosine. This now let's see. This center to center distance is D12. I can also call it V maximum. Maximum impact factor, because impact factor cannot be greater than D12. Okay? And this is B, right? So cosine alpha is simply, let me do it slowly. 1, 2, 3. This is 1 minus sine square. Alpha, this is alpha angle. Here is B. So sine alpha is D12. Is B divided by D12. And I call D12 B maximum. So this is maximum square. Okay. So we calculate this because now we want to say probability of a reaction equals to, well, if this energy, this available kinetic energy for reaction is smaller than some activation energy. So this is or some threshold energy. So only when this energy is higher than some energy, then this reaction can happen. If it's 1 only when it's greater, or we can say equal, that's it. It doesn't matter. So with this, you can then go and calculate. You integrate over all the B, or you consider, let me see. So the probability of a reaction now depends on the epsilon K, the available useful kinetic energy, and it depends on the impact factor B here. Only when impact factor is 0, I mean when it collides head on, then all the kinetic energy can be used for chemical reaction. Otherwise, this the available kinetic energy will be smaller on this equation. So now the probability of a reaction depends on the impact factor, not just the relative energy, relative velocity. So let's take this. Now let's define this part called sigma. And sigma will depends on the some energy. Relative energy. This is called a cross section. So take this probability of a reaction. Consider a distribution of a relative energy. We know the distribution already. Relative velocity. We know the distribution already. It's a Maxwell distribution. And then consider the collision can happen at different impact factor. You need to integrate impact factor from 0 to V maximum to get an average result. And this part is in the homework problem. In the homework problem, I ask you to do this step by step. But after this integration, you can calculate cross section as pi V maximum squared. This is the same here. Times 1 minus this is when we avoid. This has to do with the unit of the Rayleigh constant. Okay, we're talking about bimolecular reaction. So if your K is in the per mole unit, you can move this one to the left-hand side. Only thing we need to consider is this part. So we have a cross section like this. Then your rate will be we average this. And this depends on the kinetic energy, or say velocity, speed, relative speed. Okay? So you need to average, again, you need to average this over the speed distribution. And when you average over the speed distribution, you get a Boltzmann factor in this. That depends on the activation energy. Again, this is in the homework. So the end result is you get a rate constant. That's pi v maximum square. It's actually the same here, but you have the average velocity pi v yeah. This one is actually, but then you have exponential minus epsilon star. You get this vector. You get this vector because for reaction that do not have any that has a kinetic energy smaller than this one, there's no reaction at all. Okay, we don't even need to consider the impact factor. However, you only those reactants, those relative velocity have a kinetic energy higher than this value that will contribute to your reaction. So after this integration, only the parts that have the distributions have the energy, kinetic energy higher than the activation energy will contribute to the reaction. So that part, the ratio of molecules with that kind of velocity basically is proportional. At least it's proportional. The probability is proportional to a Boltzmann factor, like this. But this is qualitative. Actually, you can go through each step. You need to average over distribution here, and then again average over distribution here, and then you get this result. Okay. And like I said, I introduced a step-by-step homework for you to do this by yourself. Basically, the process is quite annoying. And it's useless. It's not very useful if I do it here. Annoying because basically you need to do Gaussian integral twice. And it's useless for me to do it on the blackboard like this. And I figure it will be most effective if you do it by yourself. Okay? But trust me, in the end you get this result. So what's important here is we end up with this expression that has Arrhenius behavior for the activation energy. But this expression actually is not that Arrhenius in the sense that you have another temperature factor here. So in this case, actually the rate constant A is proportional to square root of T temperature times exponential minus some activation energy divided by kVt. So we have a square root in temperature. So the behavior is really not that Arrhenius. You have this square root of T factor But the thing is, if in a small range of a temperature, in reality, actually, most chemical reaction, you don't do the reaction in a very broad range. Room temperature, 300 Kelvin, okay? Real temperature, already a very cold temperature, is 273 Kelvin. That's actually less than 10% change. So in a small temperature range, this square root factor will be quite flat. I mean, there's very limited temperature dependence in this part. The main contribution to a temperature dependence is here. Okay. And the position, actually, this term comes from where? Here. And this term represents the relative velocity, relative speed in the system. Okay. So, this non-Arrhenius behavior in a prefactor is also quite natural, also quite understandable in collision theory, because in collision theory, this collision, whether it's success or not, depends on a Boltzmann factor, Boltzmann distribution of the kinetic energy. So this Boltzmann term controls the successful rate, right, cross section. But then the collision frequency is depends on the relative velocity. It depends on the velocity, average velocity of the molecules. So you have this square root temperature dependence. So this term controls the collision frequency, how many times a collision can occur. When you increase the temperature, you have a more frequent collision between molecules. Okay? So both of them are, you can attribute them to some very understandable physical origin. So now prefactor depends on collision frequency. The Arrhenius exponential factor actually depends on the energy distribution. It's a Boltzmann factor, energy distribution. And this kind of behavior in rate constant actually is very general in all reaction rate theories. Basically, when you derive a rate constant, very often in the prefactor, you have something related to the frequency of collision. Okay, and in terms of transition state theory, is how fast this system can go through, can overcome the barrier, the transition state region. And then this Boltzmann factor controls whether or not the reaction is success. So this picture is quite general in a sense. Okay, so I'll stop here for 10 minutes. Basically, this covers what I want to talk about in terms of in collision theory.